Hello, I'm the chemistry guy. In this video we will discuss how atomic orbitals can combine to form hybrid atomic orbitals and how orbitals on different atoms can combine to form molecular orbitals. In the last lecture we examined how the periodic table describes the electronic configurations of the atoms. Each row of the periodic table corresponds to the principal quantum number n, 1, 2, 3, and so on. The first two columns on the left represent electrons being put into an s orbital. The columns on the right are for electrons being put into p orbitals, again with the exception of helium. And in the center are electrons being put into d orbitals, but these d orbitals have a principal quantum number that is actually one less than the row. So starting with potassium, we would put electrons into the 4s orbital, then they would go into the 3d orbital, and then finally into the 4p orbital. Okay? Whereas down here, for the lanthanides and actinides, these are actually electrons being put into the f orbital that has a principal quantum number 2 less than the row. So starting with row 6, again, the first two electrons go into the 6s orbital, then it goes into the 4f's, then the 5d's, and then finally the 6p's. Basically, this is what the orbital energy diagram looks like for the atomic orbitals, and we can fill them up from the bottom for each element, okay? Starting at the bottom and working up is called the Aufbau Principle. So we're now going to fill up this orbital energy diagram with some of the atoms that we've talked about before. So hydrogen, which has one electron in the 1s, puts it down in the bottom. Helium puts a second electron in the 1s, but if you notice, one of them is an up arrow, we call that spin up, and the other is a down arrow, that spin down. Lithium has, again, both electrons in the 1s and a single electron in the 2s orbital. Beryllium has 4 electrons around in the neutral atom, and so the first two electrons go into the 1s orbital with opposite spins, and the second two electrons go into the 2s orbital, again with opposite spins. Boron puts its 5th electron into one of the 2p orbitals. Carbon puts 2 electrons into the 2p orbitals, and they are in different orbitals, both with the same spin. And nitrogen has 1 electron in each of the 2p orbitals, all with the same spin. Oxygen now has to pair one of its outermost or valence electrons into one of the 2p orbitals, while as the other 2p orbitals each have a single electron. Fluorine has 5 2p electrons, and so 2 of the orbitals have a pair of electrons and one of the orbital has one. And finally, neon has a complete set of 1s, 2s, and 2p orbitals, all with 2 electrons. Sodium, which is now in the 3rd shell, or starts putting electrons into the n equals 3 quantum number, has 1 electron in the 3s. As you can see, if it loses that electron, it will look like neon, and that would be very good. That would be very, very stable. Okay, this continues, and you continue to fill them up from the bottom up. And whenever you've got a bunch of orbitals that are all the same, like the 3p's, you put 1 in each before you start pairing them. Remember that whenever possible, an atom would like to look like a noble gas: helium, neon, argon, etc. In other words, it would like to either gain or lose electrons to form ions, or form bonds so that all of the electrons in its outermost or valence shell are paired. So for hydrogen, 2 hydrogen atoms can come together And you can either add the two 1s functions, as we've got down below. These are the two 1s orbitals on each hydrogen, and you can form a sigma orbital, which is bonding, or you can subtract them to form a sigma star orbital that is antibonding. An orbital energy diagram looks like the following. Here we've got the hydrogen 1s at a given energy, okay, and the second hydrogen also has a single electron in the 1s. Now when they come together, the electrons are going to be of opposite spins. They can add to form the sigma bond, and the two electrons go in there, and they also subtract to form an antibond that is empty. Therefore, both hydrogen atoms would basically see two electrons around them, and it would seem like a filled valence shell like helium. It's a win-win situation. P orbitals can also come together to form what are called pi bonds. Okay, here we've got a p orbital on one atom and a p orbital on another atom, so these are the atomic orbitals. When we add them together, we get this pi molecular orbital, and that's lower in energy than either of these two. We also subtract them, okay, and basically come up with what's called a pi star antibonding orbital, and that's what it would look like. Carbon is a different matter. It has two electrons in the 2s orbital and two electrons with the same spin in different p orbitals, but needs all four electrons to be in different orbitals to form four bonds. When it forms four bonds, for example, then it will have each molecular orbital will have two electrons in it, and so the carbon will look like it has 8 electrons around it in the outermost shell, and that will look somewhat like neon. So effectively what it does is it mixes the 2s with the 2p orbitals. While doing that, raises the energy of the 2s electrons. Okay, when I form the bond, the energy goes down much more, and it ends up becoming lower energy overall. The 2s orbital can mix with the empty 2p orbital to form two sp hybrid orbitals. So here, when I take the s orbital and I add it with the p orbital, I get a hybrid orbital that looks like that, whereas if I subtract them, I get a hybrid orbital that looks like that, okay? These are really the way the hybrid orbitals look together. It's one is more on one side and one is more on the other, but schematically it would be drawn like this, almost like a p orbital, but more separated, okay? And the other two p orbitals are actually going to be perpendicular to this, one going up and down in the plane and one coming out perpendicularly to the plane. The 2s orbital can also mix with the empty 2p orbital and another 2p orbital to form three sp squared hybrid orbitals. So here I've got the s orbital. I combine it with one p going in that direction and the p orbital going in that direction, and what I end up with is three different sp squared hybrid orbitals, okay, that would combined look like this. The remaining p orbital would actually be perpendicular to the plane. Okay, the orbitals are 100 degrees apart, and they're all in the same plane. The 2s orbital can also mix with all three 2p orbitals to form four sp cubed hybrid orbitals. Each hybrid orbital is separated from all the other hybrid orbitals at an angle of 109.5 degrees. It has a tetrahedral geometry like a triangular pyramid composed of four equilateral triangles. Now, if you wanted to build a model yourself, just take four balloons and try to hold the ends together in one spot, and you will find that those four balloons will take on a tetrahedral geometry because it is the lowest energy geometry to keep the electrons away from one another. Let's look at the bonding in methane. which is CH4. The central carbon makes 4 sigma bonds, one with each hydrogen. In general, sigma bonds form first, and this requires an electron from the carbon pairing with an electron in the hydrogen, but obviously the spins have to be opposite. Carbon therefore wants 4 unpaired electrons, so 1 electron goes into each of the sp³ hybrid orbitals. The hydrogens form a sigma bond with each hybrid orbital of carbon, and therefore methane has a tetrahedral geometry. Even though we draw methane to look like this, where it kind of looks like it's sitting on a piece of paper, we must realize that it really has a tetrahedral shape or tetrahedral geometry. So there are 4 equilateral triangles all put together to generate the overall tetrahedral shape of methane. In molecules and their shape, we will talk more about molecules and their structure.
I hope you enjoyed this video, and if you enjoyed it, I hope you will support my Patreon page.